Welcome to Chapter 8, where we're going to get past atomic structure and into molecules to see how atoms interact with one another. So Coulomb's law tells us that the charge, we say Q1 and Q2, the charge between two atoms is proportional to the strength of their bond, and then the radius, the distance between them, is inversely proportional. So atoms that are smaller together can get closer to one another and they'll have a stronger bond. So which atoms has a stronger bond energy? Well, both of these, for NaCl and LiF, both of them are +1 -1 ions. So the smaller one is going to give me, the smaller set is going to give me a stronger bond. They can get closer together. Potassium, bromium is a constant here. Potassium and calcium are about the same size, but we notice that the calcium is +2 and the potassium is -1. So in this time, the charge is going to make the calcium a stronger bond. MgO and CaO, both of these are +2 -2 ions. So the charges are about the same. Oxygen is the same in both, but magnesium is a little smaller than calcium, so magnesium is going to be a stronger bond to that oxygen. And what happens here is, here we kind of have, if we can picture like an s orbital of these two hydrogen atoms. Remember, they're just probability regions. What happens is these orbitals, as they get close enough together, they start to interact, and they overlap until they kind of make a brand new thing. And this electron region is actually where we get a bond. There's a distance here where those orbitals that overlap tend to reside. That's the most stable. And it has to do with energy. So when they interact with one another, they give off energy. Here we have, you can see the atoms, it's kind of going backwards this way. Two atoms that are separated, getting closer and closer and closer and closer together. And they're more and more favorable. It's because they're attracted to each other and they're giving off energy. And then there's a certain point where their orbitals are overlapping and they're as close as they can possibly be without, now if they keep getting closer and closer and closer and closer together, well, now they're actually repelling each other a little bit. So there's a distance here that's optimum between the electronegativities of the nuclei attracting the other person's electrons versus the actual nuclei repelling one another over here. If they got close enough, they were all the way to 0, we would get nuclear fusion. Now, of course, that is possible, but energy requirements at room temperature, that's just not going to happen. So the optimum radius right here is where those attractive and repulsive forces are balanced out. Every atom, every bond has that distance. For these hydrogen bonds, that's negative 432 kilojoules. Is the potential energy of that bond. So based on their positions on the periodic table, electronegativities are a big factor in bonding. We need to rank these in order of increasing electronegativities. So the smallest one first, which is going to be the largest atom. So let me get the pen back out. Cesium is my largest atom, smallest electronegativity. And then barium, strontium, selenium, and oxygen. So oxygen is going to have the highest electronegativity. The smallest atoms have the highest electronegativities. And here's a chart that just, hey, there's a reminder. We don't count the noble gases over here. Noble gases don't have electronegativities. Fluorine, oxygen, and nitrogen, we'll note how incredibly high electronegativities they are. Chlorine is as well. Chlorine's a 3.0, but it's a little bit too big to really have some of the same effects as fluorine, oxygen, and nitrogen do, where they only have 2 shells instead of chlorine has 3. But you can just kind of see that's not a perfect trend, but the trend is there. We can give them electronegativity values. We call these, they'll just be delta values. And here's where we really get to see a spectrum between covalent and ionic. It's not an either or. There's a threshold where the electronegativity difference Here's our values. If the two atoms are the exact same, the difference will be 0. And if the difference is very, very large, then I get an ionic bond. But there's a threshold here. There's a lot of gray area where we can get polar covalent bonds. And it's not that it is either ionic or covalent, but it has more of an ionic character or more of a covalent character based on how big that electronegativity is. So there's a lot of molecules. The threshold here, some books have it around 1.9. The threshold here, when you have two atoms that have an electronegativity difference of about 1.9, 1.8, 2, 2.1, they really kind of have characteristics of both ionic and covalent bonds, especially if they're small. It's not so clear-cut as to say something is always ionic or covalent. Some are more ionic or more covalent than others. And here's a chart that just kind of shows that difference. The biggest electronegativity differences are up here. They have more ionic characteristics. The smallest electronegativity differences are down here. They have the lowest characteristics. But there's a whole bunch of molecules here in the middle that HF, for example, it's technically a little bit more covalent than it is ionic, but it can dissociate a little bit. Dissociating, like it's ionic, will give me a weak acid. This is why HF is weak. Some of it dissociates, but it still has a lot of covalent characteristics. So calculate the delta for each of the following bonds and order the set from most covalent to most ionic character. Okay, so sodium is going to be 0.9. Chlorine is going to be 3.0. So NaCl is a difference of 2.1. Okay, LiH is 1.0 to 2.1 is hydrogen. So we get a difference there of 1.1. Hydrogen again, 2.1. Carbon is 2.4. This is a very, very non-polar bond. Sorry, 2.5 is the carbon. 0.4. HC bonds are very, very non-polar. We actually consider them to be non-polar bonds, almost entirely 0. H 2.1, fluorine is 4.0. There's a big difference there, 1.9. RbO, Rb is 0.5. Oxygen is 3.5 for a difference of 3.0. So rank them from most covalent to most ionic. Well, most covalent is going to be the HC bond at 0.4, and then the LiH. It's actually a pretty covalent bond because it's so small. We'll get that one next, and then HF. So LiH is actually a little bit more covalent than HF. NaCl. And then the most ionic is going to be the RbO. Here's just another graph that shows that electronegativity difference. This is an electron cloud to show polarities and where the electrons reside. There's more electrons over here in the electronegative element. So instead of having their s orbitals, we get a little bit of an overlap of their orbitals. We get new shapes, and you can just see the disparity there with all the electrons. Here's an electronegativity dipole moment for water molecules. In general, we see that the hydrogens are both positive and the oxygens are negative. That pulls the electrons in this direction. So that arrow represents the pull of the electrons. It's symmetrical along this plane. It's asymmetrical along that plane. So we get a positive side and a negative side. So we want to be familiar with that notation. And here's just that notation again for the rainbow diagram. So it just shows the polarity over here. There's a lot of electrons by the oxygens, and the positive side is hydrogens. Here's one for a nonpolar molecule. Where the dipole moments, you can see here, the dipole moments cancel each other out. They're going opposite directions. This molecule is totally symmetrical in all directions. So those electronegativity differences, they end up canceling each other out as a whole. So this molecule is symmetrical. We're going to call it nonpolar because there is no net dipole. Here's a CHCl3. Does it have a dipole moment? Well, we need to draw it and show the orientation of it. So CH, Cl, Cl, Cl. So now we're looking at the electronegativities here of multiple atoms in multiple directions, but in general, we're just going to see, is this molecule symmetrical, and where is it not symmetrical? Well, it's symmetrical going left and right. It is asymmetrical up and down. That means my dipole moment is going to be up and down. Okay. So my dipole moment here, if I'm just looking, and it's not two-dimensional, this is a three-dimensional molecule. Chlorine in general is more electronegative than hydrogen, so my electrons are going to be going this way, and I'll have a little bit of a positive side there on the hydrogen. It'll be asymmetrical. Dipole moment going down. Determine the orientation of the dipole moment. So let's draw all of these. Simple molecules, HI, they're connected. Dot structure of iodine looks like that. Iodine is more electronegative, so the electrons are going to be going this way, and the hydrogen ion will be positive. N2, N has a dot structure like this. It has 3 lone pairs. That's going to give it 3 that's going to give that nitrogen a triple bond with 2 lone pairs on the outside. And this molecule is totally symmetrical. There will be no dipole moment. And if we look at the CClF3, carbon's always in the middle. It can make 4 bonds. We're going to do a lot more of these shapes here later. CClF3. Now we've got a situation where the chlorine is asymmetrical with the fluorine, up and down the way I've drawn it. And in this case, the electrons are going towards the fluorine because fluorine is more electronegative. So the dipole moment is going away from the chlorine. And then, oddly enough, even though we started the year in chapter 1, because we kind of needed to get through some things, we talk about ionic bonding. We do some of the covalent shapes and structures, and we go back into the ionic ones as well. So to determine ionic strengths and ionic bonds, we go back to Coulomb's law again. Q1, Q2 over R. Charge and distance, and they make ionic bonds based on this formula. Anything we have that's ionic, we can compare these and determine the formula. This just says what is the formula for these. So we don't necessarily need Coulomb's law for this, but just when they form ions based on everything we know about their atomic structure, we know that potassium is +1 and bromine is -1, so there will be a KBr +1, -1. Strontium and fluorine is SrF2. Aluminum and selenium is Al2Se3, get you to +6, -6. Barium and oxygen, barium is a +2 ion, oxygen is a -2 ion. So if we need to rank and judge them, similarly we can use Coulomb's law over here, Q1, Q2 over R, but simple charges will just say, hey, what are the charges that, we've known these since week 1. What are the charges of these guys, and how can I make an ionic formula out of them? And then we also, since we're talking about ions and bonding, the electronegativities or electronic configurations come back up of stable ions. And we just remember that they can be isoelectric with one another. The positive ions will lose electrons to empty their shell because it's stable. They're really easy, low energy to take those off. And the negative ions release a lot of energy to put them back on, so they're all isoelectric. So all of these guys have 10 electrons. They're all isoelectric. Different neutrons in the different protons. Protons in the nucleus pulling in men, of course. Their electron configurations are the exact same, and that's kind of the basis for how the atoms make ions, and then they'll start bonding with one another accordingly.